Hey, welcome back. Ever wonder how to make sense of the entire field of computer systems? I mean, everything from the little chip in your phone all the way up to the global cloud. Well, today we're going to build a really simple but super powerful way to think about it using four foundational pillars that we've found in decades of research.
So let's just jump right in. When I say computer system, you probably picture your laptop, right? But the reality is, it's so much bigger than that. That term actually covers this huge scientific field that's all about the design, the analysis, and the operation of pretty much every computing device you can imagine. So what are the big ideas holding this whole field together?
To figure that out, we went straight to the source. We dug into thousands of academic papers published over the last, several decades. We looked at all the ones classified under general theory of computer systems. And by tracking the main ideas, the core concepts that researchers kept coming back to, a really clear structure starts to emerge.
And this is it. The whole field really boils down to four distinct but totally interconnected pillars. First up, you've got the physical stuff, hardware and architecture. Then you've got the brains of the operation, software and theory. Third, how all these systems talk to each other and work together, communication and concurrency. And finally, the things that keep it all running fast and safe, performance and reliability. Together, these four things, they explain pretty much everything.
All right, let's get into pillar number one, hardware and architecture. This is the bedrock. This is where it all begins. We're talking about the actual, tangible, physical parts of a machine and the big ideas that decide how they all fit together.
Looking at the research, these are the terms that just pop up over and over again. You see things like processor design, that's the brain, right? Then there's memory hierarchy, which is just the system of fast and slow storage. And of course, digital circuits, and VLSI, which stands for very large-scale integration. That's basically the magic of cramming billions of transistors onto one tiny little chip. This is the physical gut of any computer.
Now this is where it gets really interesting. This slide captures this huge debate that was happening back in the 90s. The question was, do you build a processor that understands really complex, powerful commands, that's CISC, think of the classic Intel Pentium chips, or do you go the other way and build one with a smaller, simpler, but incredibly fast vocabulary? That's RISC, like the PowerPC chips that used to be in Apple computers. This constant battle between complexity and speed is a challenge in hardware design that just never goes away.
Okay, so let's move on to pillar 2 and see how everything builds on top of that. We've got our physical machine, but right now it's just a box of metal and silicon. It doesn't do anything. So what's the logic? What are the instructions that bring it to life and actually make it do stuff? Well, welcome to the world of software and theory.
And right at the heart of it all is the operating system. The research papers call it the master controller, and that's the perfect way to think about it. It manages literally everything. It decides which program gets to use the processor, how all the memory is shared. It's the traffic cop. It's that crucial bridge that lets your apps, your browser, your games talk to the hardware we were just discussing.
So how does an idea in a person's head turn into an action on a machine? It's this process right here. A programmer writes in a language that we can actually read, like C or Java. Then a special program called a compiler acts like a universal translator. It turns that human-readable idea into raw machine code, the ones and zeros that the processor can actually understand and execute. This whole process, turning abstract thought into physical action, is really the magic of software.
On to pillar 3. Think about it. In today's world, a computer working all by itself is, well, it's pretty rare. The real power, the game-changing power, comes from connecting them and getting them to work together. And that brings us to the pillar of communication and concurrency.
One idea that you see constantly in the research, especially from the 90s, is message passing. And it's a really simple but incredibly powerful concept. Basically, separate computers or programs coordinate what they're doing just by sending messages back and forth. It's like a super fast digital postal service. And this one idea is the foundation for everything from supercomputers to the internet itself.
And you can see how that one idea evolved right here. Back in the 90s, the big thing was massively parallel processing, getting hundreds of processors inside a single giant machine to talk to each other. By the 2000s, that expanded into grid computing, linking computers across entire universities. Then in the 2010s, that became the cloud computing and huge data centers we all use today. And now, we're even seeing decentralized systems like blockchain, which is really just a wild new way for systems to coordinate with each other.
And that brings us to our final pillar, performance and reliability. Now this one's a little different. It's not about a specific part. It's about the essential qualities that make a system actually useful and trustworthy. These are the things that cut across all the other pillars to make sure our systems are fast, dependable, safe, and efficient.
And this table breaks it down nicely. When we talk about speed, researchers are focused on things like benchmarking to measure it and make it better. For dependability, they're working on fault tolerance and error recovery so our systems don't just crash. For safety, that's all about computer security. And a really big one lately is efficiency, especially when it comes to power.
You know, this focus on energy efficiency is actually a huge shift in the field. For decades, the name of the game was just raw speed at any cost. But if you look at the more recent research, that's totally changed. With phones that have tiny batteries and data centers that have insane electricity bills, power consumption is now a top priority. A system that's super fast but drains your battery in 10 minutes or needs its own power plant, that's just not a good design anymore.
So let's put it all together. How do these 4 pillars actually combine to build the tech that we use every single day? Let's take a look at a modern example.
Just think about any cloud service you use, online storage, a streaming app, whatever. It's a perfect example. It's built on the hardware of massive data centers. It's managed by the software of virtualized operating systems. It depends on communication to send data all over the world. And it absolutely requires that 4th pillar of performance and reliability to be fast, to be secure, and to be energy efficient. You see, it's all 4 pillars working together perfectly.
Which brings us to one last really fun question to think about. As technology keeps changing, what's the 5th pillar going to be? Will it be AI hardware code design, where we build chips specifically for intelligence? Or maybe it's quantum computing, which would introduce a totally new type of hardware and theory. The research is pointing in some of these directions, but only time's going to tell what that next foundational pillar of computer systems will be. Thanks for tuning in.